Hey, welcome everyone to my continuation of what are my favorite theorems. Very biased collection, of course, as usual. Today I would like to go into a bit more details about planarity testing. So how can you, find a planar embedding of a graph, or how can you test whether a graph is planar or not? Because it's kind of fun. It's like ridiculously fast and not so difficult. So I should say here, I'm showing you, I think, as far as I know, kind of the classical fast algorithm. By now, there's more than one algorithm to do it. And it's kind of remarkable that they're all very fast, and there are many ways to do it. And I kind of always feel like this is something that is like impossible if you try to do it by hand. Whether you really should run this algorithm by hand, probably not, but it gives you a hint at least how to do it by hand. We'll see. It's kind of remarkable, as we'll see. So a planar graph, a graph is really just this thing here. It's an abstract beast. It's a collection of, A is connected to C, like this one here. A is connected to D. A is connected to B. A is connected to E, something like that. Just a collection of, edges, if you want, and how they are connected. So graph theory is only about, or graphs are only about connectivity. So a priori, there exists no picture of them. But what people always do is they always draw something, like this is a drawing of my graph down here, right? And this is also a drawing of my graph. And the planar graph is one that can be drawn in the plane without edges crossing. And that's usually not obvious at all, because if you just kind of draw it naively, most of the time you will end up with a picture that is kind of like this. And this is not a planar drawing, because you have intersecting edges. Here, for example, is intersection, here's an intersection, whatever. But there is a planar drawing. So this graph is planar. And that's exactly the point where this looks so tricky, because you kind of would need to find a planar embedding to verify that it's planar. That's how it looks like. And just trying to do that by hand kind of needs a good geometric intuition, which vertex should go where. And it's a bit like annoying. And I kind of always was very surprised. I was literally very surprised when I learned that this can be done very quickly, in a sense that every usual computer algebra system should have something like it is planar that you just type in, and it will tell you whether a graph is planar in no time. Anyway, so just to do this by hand, because we have so many options how to place vertices and edges, it's like, it's always like, looks like it's really, really, really tricky. And the question is, can you actually efficiently do this? So is there some reasonable algorithm that decides whether a graph is planar? And it's really not clear at all, right? Because you can somehow place the vertices wherever you want. You could place the edges however you want. So how can you make sure that you will find a planar embedding of something? And it's kind of remarkable. It uses the Jordan curve theorem, but we'll see. But anyway, so let's say you have some graph here, like this one, and it's very, very large, K7, and you wonder whether it's planar or not. And you just look at it and you see, this graph has a lot of edges. Like a lot of edges compared to the number of vertices, like a lot of edges. So that should ring a bell, because planarity, edges are not supposed to cross, right? It's difficult if you have many edges. So a graph with many edges is unlikely to be planar. And that's actually a better statement. And I wasn't aware about this statement until I looked up this algorithm, which is kind of extremely easy to prove. You can just do it in any class on graphs. Actually, it's really, really easy. And that's a bound on the number of edges, such that your graph, if the number of edges is bigger than that bound, your graph is not planar. So the precise statement is the following. So if G is planar, then the number of edges, so E, let me just write E, is smaller or equal to 3 times the number of vertices. This was supposed to be a 3. Give me another try. 3 times the number of vertices minus 3. Right? So only few edges compared to the number of vertices. For example, for our complete graph here, this is the number of edges, n is the number of vertices. So you get this equation that n times n minus 1, which is a polynomial of degree 2, should be smaller or equal than a linear term. And this is usually not going to happen. And you can just solve and you see that this one holds if and only if n is smaller than 6. Okay. So you can immediately see from this bound that K7, K8, K9, K10, whatever, they're not planar, and kind of a random graph that you just have many vertices and very many edges. So usually you have many or more edges than vertices. Usually they're not planar. And you can just immediately get this from this bound. which is like remarkable. I wasn't aware. So I just want to point it out again. A really easy bound in the number of edges and the number of vertices. And this is kind of cool. And we will use that kind of obviously if you want to planar testing. Just the first thing you did is you count the number of vertices, count the number of edges, and you can immediately say, no, it's not planar if there are too many edges. So that's always already really good. And the next step, so, okay, let's say you end up in this gray area. So the bound is clearly not optimal. And let's say you end up in this gray area where you really don't know if it's now planar or not. And the idea is to make it into a tree because trees are always planar. So you take your graph and you place it in this tree form. So these guys are called palm trees. They're just some tree form like this. So you find the spanning tree. You can do this with DFS, which runs kind of really quickly. It just runs in number of vertices plus number of edges, and it will find a tree. So like an object like this, a tree. So there's a spanning tree, like this picture here, the bone of the palm tree, and everything that creates a cycle is the backwards edge, right? So I'm not talking about this needs to be oriented or anything, but let's just orient it so it gets easier to see. So everything kind of grows in the palm tree, and then the cycles are all backwards edges. And that thing is called a palm tree because it looks like a palm, I guess, where kind of the leaves hang down in some sense. Anyway, so this is called a palm tree. You get that really cheaply in just, if you haven't seen this notation, the Bachmann-Landau notation, I will explain that in a second. But you get that really cheaply. And essentially what you can do is, so this is kind of really easy. And essentially what you can then do is just do planarity testing, which I'm going into details in a second, like on the last slide, essentially by, well, picking out a cycle and break the graph along the cycle and test on the smaller components, running the algorithm recursively, and then kind of check whether you can put them together. And this actually works, and this gives you the famous algorithm by Hopcroft and Tarjan, which is by now quite old, and most computer algebra systems should run a version of this. I said again, you create this palm tree, which you can do very, very quickly. You take one of the backwards edges, cut the tree along that edge, so break it apart, and then just run the algorithm on the smaller pieces to get a yes or no, and then have some algorithm to put them together. And this decides a planarity for you and actually even finds a planar embedding because, well, this guy rearranged correctly will then be the planar embedding. So to summarize, I will give you more details for the algorithm in a second. This algorithm runs actually in O of n, where O really just means the algorithm doesn't grow faster than whatever you see inside. So F in O of G means F grows no faster, like really this picture, than G from a certain point onward. So there's always kind of this part here, which we ignore. And then from some point onward, F will always be below, let's say, some scalar times G, right? So that's the capital O notation. Actually, fun story, this is Bachmann-Landau notation. It's supposed to be an omicron. So there's also capital theta and capital omega, and this is supposed to be an omicron, so the Greek letter, but turns out that an omicron is not distinguishable from an O, so people call it the big O notation or the capital O notation, whatever. Anyway, essentially what this is, it gives you an indication on the worst case scenario of your algorithm. And usually, well, this is roughly the thing one should have in mind. So constant time, O of 1 is just really fast, and factorial time, O of n factorial is just really shit. And yeah, right, linear time is just surprisingly fast. So it's linear in the number of vertices. And essentially what happens here is, well, we had just one thing we really ran, and this was V plus E, but E is kind of bounded by V, right? So actually it's only in V. And we even find an algorithm if it exists. So this algorithm, which I'm going essentially sketch how it works on the next slide, is just the main, or the oldest at least, the classical planarity testing algorithm. And yeah, this is just absolutely fantastic. It checks planarity, which looks like impossible, in a ridiculously fast, like O of n, like a linear time in the number of vertices, which is really, really remarkable. And note that you just kick out all graphs that have this number too big. So the number of edges actually doesn't really play a role. But if the number of edges is too big, you just declare it to be non-planar anyway. Okay. And this is roughly how the algorithm runs. So keep in mind, we kick out everything with too many edges from the start. And then we create a palm tree. So here's a palm tree. And we take one of the backwards edges. Let's say, well, this was a bad color choice. Let's say we take this backwards edge here. And then we have our palm tree, which goes all the way like this, right? And we can just take this cycle in our palm tree and cut it apart into smaller bits. So we have this S1 here, you have this S2 here, the S3 and S4, which just hang around now as smaller bits. And you run the algorithm on them and find a planar embedding for them. Okay. And then what you do is, if any of them is not planar, you're dead anyway. But if all of them are planar, so if something is non-planar, just return not planar, because if a subgraph is not planar and the whole graph is not planar. Anyway, so let's assume that it is planar. Then you kind of have this natural ordering, let's say from bottom to top. So this one hits its next, and S4 hits next. And you just put them in one by one. And whenever something doesn't fit, you can somehow try to flip it over. So what you can do here, if we just, this is how the algorithm works. And if flipping over doesn't work, then it's not planar. So S1, perfect. So S1, perfect, works. S2, we can just put it on it, works. S3, we can just put it on it, works. And now S4 has a conflict with S3 and S1. So what we can do is we can just flip S3 over. So S3 will be then somewhere here. Then you can flip S2 over. So S2 will be then somewhere here. And then you can flip S1 over, and S1 will be somewhere here, and S4 fits. And you just run that algorithm. If something doesn't fit, flip everything over that is in that has a problem with your S4 in this example. And if that works, continue. And if that doesn't work, then well, stop. And it's not planar. It's kind of really easy, right? You create the palm tree, you cut it along the cycle, you have different smaller pieces that you can check using the algorithm recursively, and then you just put them together and play this flipping game, whether there's some flipping that actually makes it work. And this is kind of remarkably simple and runs in O of number of vertices, which is like easy. Whether I would recommend to do that by hand, maybe not. The flipping over is a bit annoying. Maybe with an iPad, or if you can write it on your tablet, it's a little bit easier than whatever I write it on paper or something, because you kind of need to erase everything all the time. But anyway, it's certainly a good idea to create the palm tree. And from the palm tree, you can maybe even eyeball directly whether a graph is planar. Anyway, I hope you enjoyed this video, and I also hope to see you next time.